Today's presenters are Bob Meyer and Larry Ibarra. Larry is the Quality Assurance Manager at Royal Flex Circuits, and Bob Meyer is the Vice President of Operations. Both are around 40-year veterans of the printed circuit industry and have been involved in the manufacturing and design of flex circuits for probably 50 years. So now I'm going to go ahead and turn it over to Larry and Bob.
Well, first of all, I'd like to thank everybody for joining the Royal Flex webinar today. This is Larry Ibarra, and you just heard from Bob Meyer. And we'd like to start out today. Royal Flex has over 30 years experience in producing flex circuit boards. And some of this will include quick turns. Our standard quick turn is generally 3 to 5 days, depending on complexity and number of processes involved, i.e. stiffeners, finishes. Also, single flex, double flex, multi-flex with 3 layers or more, rigid flex up to 12 layers, and we also do assembly. Some of our current customer base are Nokia, Boeing, Thales, Medtronic, Motorola, Siemens, Tesla, Raytheon, L3, Harris, Qualcomm, Sony. During our 30-plus years with our business, we have worked with our customers to build up our knowledge database so we can produce both functional and reliable product that will exceed customers' expectations. Here at Royal Flex, one of our main goals is to have a good working relationship with our customers to be responsive to the needs. One thing that we would like to emphasize is that when you're inquiring about having a product built, whether it be flex or rigid flex, it's very important that we, the manufacturer, receive good, clear, concise, detailed data about the product. This will ensure that the end product meets your expectations. Flex printed circuit boards. Topics to be covered today for the webinar will be overview of flex options, tips on designing with flex circuits, material considerations, and documentation of best practices. A flex circuit is a technology for assembling electronics by mounting electronic devices on flexible plastic substrates, which as polyimide. Flex circuits are often used as common connectors in various applications where flexibility, space savings, or production constraints is a factor. Advantages to flex: potential to replace multiple rigid boards and or connectors. Single-sided circuits are ideal for dynamic or high applications. When it comes to comparing flex versus wire harness, flex circuits has many cost-related advantages. Space and weight reduction. A single flex circuit can replace several hardboard cables and connectors. A flex circuit will also give you a robust connection. Flat foil connectors dissipate heat better, carrying more current than round wires of the same cross-sectional area. Conductor patterns in a flex circuit maintain uniform electrical characteristics. Things like noise, crosstalk, and impedance can be predicted and controlled. Fast assembly. Flex circuits eliminate the need to color code and wrap bundles of wire, therefore reducing the total installation cost, not to mention the dynamic flexing of the PCB. Flex applications. Some of the applications for flex: medical devices, keyboards, telecommunications, industrial, commercial. Flat, flexible circuits are able to fold into nearly any shape due to their flexibility and smaller size. Although they are small and lightweight, they are durable and capable of handling high density. Materials in flexible circuits include bare copper, acrylic, and pressure-sensitive adhesives. The typical application of flexible circuit includes plotters, copiers, cell phones, and printers.
Some of the types of flex design that we build on a regular basis: single-sided, with dual access. You can have cover coats that open the top side only, or we can build them where you can access one layer from either side of the board. Double-sided, pretty standard, plated through. We do flex coils with wraps of copper in certain applications, and then the final is the multilayer flex, where we can do any number of layers in your package that you need. Sometimes they run redundant traces, multiple ground shields, those type of things. So those are the most common styles of board. Considerations when you're designing, again, is stack up. What area are you trying to fill? Where does it got to go? So how thick can the board go? Materials. Typically, it's a polyamide film we're using, and whether or not use adhesive or adhesiveless attached copper, FR4, stiffeners, those type of things. What temperature is PCB going to endure? So that kind of drives what materials and finishes to put on. And then final is the cover lay versus solder mask, and often we use a combination in order to meet the real tight features that are required in some of the tighter packages. And then last, we do impedance and impedance control work. Again, it comes into our shielding and ground planes, and how important the signal integrity is to your end use. Next one, we're talking about bending. Pretty common, that's the most common considerations. You got your semi-static application where the flex doesn't actually flex constantly during the movement, but maybe flexes to put it in and out of the box or the application, and it's just bending. Dynamic are the ones where you're going to see in printers and those types of things, where you got scanners where it's going to move back and forth constantly, and some other electromechanical equipment where drawers are moving in and out, those types of things where you'll see the dynamic application go. And then the static is just, it's going to be installed one time, form fit into a fixture, and boom, it's never going to move again unless you, for the life cycle of the product. A little bit here. This connector, we put that in on a separate sheet because it's very, very common application. Zero insertion force. The most critical call on that is the thickness. Right about a 12 mils, 3 millimeter thickness. Very common. We use a variety of stiffeners and adding materials as needed to create that thickness. So depending on what your requirement is for the rest of the part, we'll adjust a stiffener on the back side of that zip to give you the proper thickness so it plugs in cleanly. This is a big part of when we're doing our construction. Kapton thickness, that's going to affect the bendability, how the thicker it gets, the less flexible it becomes. But in some requirements, the strength of a thicker Kapton helps out, higher heats, those types of things. Our other consideration is how the copper is attached to the Kapton film, the flex film. Common was an acrylic adhesive or an FR4 adhesive that they use to bond the copper to the Kapton substrates. It's very flexible, but the Z-axis isn't as stable as adhesive-less construction, where the copper is actually attached through a processing and bonding process. In some cases, it's actually splatter-coated on there. This type of construction or material is definitely recommended overall. It just seems to perform better, we've seen over the years. Less variation than you get with the adhesive products. When you go to a rigid flex and those type of builds, we're not really talking about today, but adhesiveless is the name of the game there. And it's all about the Z-axis expansion and trying to reduce that. Plus there's a little bit better bond, we think, with some of the other materials when we use adhesiveless base materials. Copper thicknesses, we use anywhere from 1/4 ounce up to 4 ounces we have in stock. Definitely that affects your bendability, so it really depends on your design and how much current you're putting through, those type of things. So we do some of the thicker coppers, but they're generally not on a dynamic build or on a something that's going to be moved a lot. It's definitely related to how much power is going through. And then last is on the ground plane layers, crosshatch versus solid. We still see quite a few solid ground planes, but more and more we see the crosshatch either at a 30 degrees or a 45-degree angle. We can pre-calculate that or predict that with our impedance layers, and it definitely gives you a little more flexibility going to the crosshatch ground planes. We definitely have seen that. Best practices, and we're talking stiffeners and cover lay versus solder mask. We do a combination of stiffeners quite often. The picture up there, if you see on the right, it shows you 2 rigid stiffeners, one on this end, this is drilled and tooled, another one on this end, and then below that, that's a Kapton stiffener, so it's going into a thinner, either a connector, we're trying to hit a certain thickness, and then the rigid ones are just there to support the mounting holes and fixtures so they can tie it down. So when you're thinking about stiffeners, what's it going to be in, and how thick do you need to be? We tend to see the Kapton being used where it might tear, where there's a transition point of some type. You know, rigid is for the through-hole connectors. We see those quite a bit, or if they just want a real heavy backing for a number of reasons. But it is to give it more reinforcement. The cover lay versus solder mask. The example down here on the lower right, you can see part of the board has a cover lay on it where they're going to do the bending and the flexing, and then the rest of the board, even though it's a flex circuit, we've put mask on, and the reason being is it has a lot of tight features with some small dams, maybe 3 and 4 mil dams between the solderable areas. And what we're trying, we can't laser cut that small of a feature, so we tend to use it as a mix. So where you're going to bend it, we're putting Kapton, and then where you're going to be assembling and you have your caps and your small components, we will put a solder mask, and then a lot of times behind that we'll reinforce that area. But solder mask is a good option on your real small features and parts. So. Next one, and we started to cover this a little bit, cover lay versus solder mask. Solder mask holds up well in flex in certain situations. In a real dynamic bend, you know, it will wear out a little quicker. The advantage is, you know, with the cover lay, it's a little more durable, a little stronger. It's going to give you a little more tear strength. The mask, though, it works very well. We use an amber that blends in right with the cover lay. And again, I go back to defining real tight assembly areas. I think it works much better. When we can't define a real small feature in cover lays, we tend to have to do a gang opening and open it as a bigger box, and then you might have some solder issues and solder migration when you're doing your wave solder. So we'll use a combination quite often. Yeah. And then this is just kind of covering this next slide, what we're talking about, to continue that with you know, the solder mask is definitely thinner, and it really helps in the bridging of closely spaced pads, traces, and those types of things. Our choice, you know, it's really driven by design and what you need to assemble. But again, anytime we can define those real small features with mask, it definitely improves assembly for the contract manufacturers for sure. Bend radius. Now the bend radius is how far you're going to bend it. Here's a basic, you know, IPC guideline. That, you know, the bend radius should be 6 times the overall thickness, which, you know, the example there is, you know, 12 mils times 6. Multilayer, you get a little less bend radius, and it's usually thicker and just not quite as flexible. Some instances, you probably will go beyond that, much smaller, because where it has to fit. If it's not in a dynamic situation, you'll probably be okay because you're not going to wear it out. But you can get cracking if you over-bend a part or fold it, so we don't recommend that. I mean, if you're bending something or folding it and you have to move it back and forth, eventually it's just going to break. So you have to be careful on how you design and the lengths and where you're tracking your part through, you know, the various configurations in your setup. But you can probably push those limits a little bit, but you have to be careful in what kind of situation that you're putting the flex in. Recommended finishes. Now, we see more and more variety. Generally, the two most popular is the top one, the Enoch. That eliminates any lead from the process, so it's RoHS compliant. It's easy to solder to. It keeps a nice clean surface, and it holds up real good on the shelf life. The second one, probably just as popular, down towards the bottom there, is the hot air solderling, which your typical 60-40 tin lead mix, and that's been used more than anything else. And there's a little demand for it. It does have lead in it, so there's some applications that won't accept that. Now, Enoch, we use that when there's wire bond applications from the customer. For wave soldering and stuff, there's really no use paying the extra money for that, but it's a good process, and they get a good bond strength, good pull strengths on the on your wire bonds. Electrolytic hard gold is generally used for contacts and plug-in connectors, those type of things where you would be putting into a hard connector. With the zip connectors that are most common, it generally isn't necessary on those, so Enoch works just fine. But the on some of the older styles, the hard gold, especially if you're going to be plugging it in and out quite a bit, that definitely warrants using that. Immersion tin and immersion silver are both antiox type of covering for the copper. It doesn't have long shelf lives, and it's for people who want to assemble right away. But generally, like the tin immersion is not recommended because it does have the dendritic growth, and you can get the tin slivers and those types of things. But again, that's not a very common finish. We'll see a little more silver immersion than tin, so I don't see much of tin. And again, we covered the hot air solder level. The last one there is the lead-free. We do see a little bit of that, and there's still some demands on getting the lead-free solder, and that's available if that's what you require for your finish assembly. And you can see some examples down there. This one down here is just an OSP, organic cover where we just dip it, keeps it from oxidizing. They generally assemble those really quick. The example up here on the right is it's an Enoch finish, and it's typical what you'd see with a little flex. Down here on the left, now there's a lot of contacts. We've made those where those for the push button type boards. we'll do a selective a nickel, electrolytic nickel gold on those. I'll probably etch off bus bars or use a type of connection, but those work where you're going to have a button pushing against it constantly, so contacts will hold up much better. And then right here is another example of an Enoch finish on a small part. So the surface finishes, again, it comes to how you're assembling, what you're assembling, but Enoch and the hot air leveling pretty much cover the majority of what you'll ever need for surface finishes.
Okay, flex circuits give you a maximum flexibility when designed properly and are a good choice for uses in wire harness situations. Usually lightweight and compact to accommodate today's compact electronics. The objective should be to achieve the designer's goals and to obtain all benefits of the Flex PCB at the lowest possible cost. So at this point, we'd like to thank you for joining in our webinar. And we're going to take some questions right now. If we cannot get to any questions, please email any other questions to the address below. That's bob.m@royalflexcircuits.com or larry.y@royalflexcircuits.com. Okay, we'll take some questions now.
That goes back to Lisa.
First question.
Here, I'll answer this one. It says, why would you use a Kapton stiffener over a rigid stiffener? The one reason, especially we work with a lot of quick turns, using a Kapton stiffener to hit your overall thickness, which I explained we do sometimes with the zip connectors, kind of quickens the process for us. We can generally press a Kapton stiffener on at the same time we do the cover lay, so that reduces a press cycle. So in turn time, you know, that saves us maybe 6 hours of processing and the, you know, laying up and going through the press. It also saves us a little time at the back end because we can laser route Kapton stiffener at the same time we laser route the flex itself. We generally don't use steel rail dies and those types of things anymore. So that really helps. When we go to a rigid stiffener, it's definitely a separate lamb cycle, and it's also a mechanical route. So we'll do part of the route on the laser and then come back and do it on a mechanical. So it's really a time consideration. I know there's some instances where the designers just like a more robust or a little stiffer stiffener, so to speak. So FR4 is their option. Once you get over about 10 mils, then the Kapton stiffener is not as viable. It becomes a lot more expensive, that material. And then yeah, we're getting into the point where the FR4 stiffeners will probably be more helpful when it's thicker. And then we see some stiffeners up to like 125 mils thick. So you know, that wouldn't be, you can't really replace that with Kapton. So generally the thinner, like I was saying, 10 mils and under, Kapton's to me is a better way to go. It gives you enough support for your assembly. And that's why, you know, we would prefer a Kapton on some situations.
Next question.
Question?
So I can help you there. We have a question from Michael. He said that if you had a slide for trace thickness and clearance limit, could you put that up? Oh, he wanted to see if we have a slide for the thickness and clearance limits. And actually, we can send out the whole presentation to you, so you have all of that information.
Okay. So what was the question about? That's more of a design question. What's our design parameters?
Right. Right.
Okay.
There's another question from John here. He's asking, on a multi-layer flex, can one or more layers be plated Enoch prior to cover lay application?
Yes. We've done that where we expose an inner layer to the surface, maybe in a connector, and then the other end is thicker. So we will do Enoch on that. Putting Enoch across the whole board on a flex is generally not recommended under the cover lay because you have nickel there, and nickel can crack, could cause you cracking on there. So we've done it. If it's in an application where you're not bending it, yeah, then there's no problem. But if you are bending it a bit and you put Enoch under there, there's a higher chance of getting cracking and maybe some intermittent opens. So, but the answer is putting the Enoch on the inner layers. Yeah, that's pretty common. Generally, it's when they have a tip that's exposed or maybe an appendage coming off the flex that only has layer 2 on it. Let's say layer 1 and 3 are part of the other end in the package. So it's pretty common to do that, and we can do that as needed.
Okay, and then there's a question from Martin. He says, I have a client who wants to make a long chain of sensors using a double-sided flex board, 10 mils wide. What is the longest length that could be made with this width?
How wide was that again?
10 mils.
Oh, 10 mils wide. Wow. Then we've built up to a 33-inch flex. Being that it's double-sided, you know, we can, and depending on the trace width, we have various options. But as far as the length, our largest panel we run through now is on a 36-inch panel, which pretty much makes it, you know, about a 34-inch part. So we can do pretty long flex and open various, you know, attachments along the way. We've also done it where they kind of daisy chain, where they can put attach multiple flex together after they're built. We also have a way where we can kind of, I guess, snake it, where we can make a longer flex on a panel by essentially making U-turns going back and forth across the flex, and then you unfold it kind of like the old paper doll once we finish routing it, and we've made pretty long flexes. I've seen flexes up to 60 feet long done in that way. So there's a few different ways you can approach that. We'd have to look at the design and the line width and those type of things, but you know, we have different options for really long flex.
Okay, here's another question. Can you do BGAs?
Yes. We've done some unique BGAs on flex. We will actually, we don't do copper fill or epoxy fill on that, which creates a little bit of an issue because they like to have it sealed under there. But we have a process where we actually laser drill from the bottom side. We don't penetrate the top side pad. We just connect to the bottom of it. And then we image BGA, give it finish, and you'll have perfectly flat pads and vias on the surface, and you'll get a good connection to your bottom layer. So again, we'd have to look at the design, but we do have BGAs. And then what we do generally on the back side is they'll put a stiffener in behind that, Kapton or sometimes a rigid to give it a little more reinforcement. But we've built quite a few of them with BGAs.
All right, it looks like we have one more question here. With 2 ounces of copper, what should be the minimum trace-to-trace clearance?
I guess it depends a little bit on the width of the trace. You can go down a 2 ounce down to about a 2 mil air gap. So we would want to see a design come in at like 3 mils, and then we have to adjust our compensate for our edge factor. So we would beef your line up a little bit, and then when we etch, we'd end up down around that 2 to 3 probably would be the smallest that we do as far as an air gap there. But it depending on the line. With 2 ounce copper, we can hold a line width pretty well. We're only going to lose about a half a mil per side through our Q-prick process, so we can hold some pretty tight air gaps. But with 2 ounce, we can hold it down to about 3 finish.
All right, well, I think that's all that we have right now. Again, if anyone has further questions, if you have design-specific questions for Bob or Larry, just go ahead and email them directly. And we will also be sending out this presentation to everyone that attended today. So we thank you all for your time and look forward to working with you in the future.
Thank you very much.
Thank you.